All right. So, in your project, what you're going to do is build a spam classifier. Right? And a spam filter is basically a text classifier just applied to the decision of whether or not something is spam. But you can apply text classifiers for a lot of things. One of the things that you can use them for is to automatically categorize news stories by topic, right? Or automatically categorize web pages by topic. And in some ways, the topic classification problem is more interesting because it's more challenging, right? I have a lot of classes. So what I would like to do now is look at specifically how we build a naive-based classifier for text, because there's a few more things in addition to just the generic naive-based classifier, and then see what happens when we do apply it to text, okay? So, let's say that, for the algorithm that I'm going to describe here, for simplicity, for the moment, let's just assume we have only two classes, right? And the extension of this for, any number of classes is straightforward, right? So let's just say we're trying to decide whether the document is interesting or not. So positive means interesting, negative means not interesting, okay? The first decision is, how do we represent our documents, right? And notice that, these days, the answer is obvious, but it's not clear, back when people started doing this, how I take text and I map it to a classification problem, right? In classification, what I have is a vector of attributes, and in text, what I have is, language, right? And what people did was sort of like the simplest thing that you could do was just think of the text as a bag of words, which sounded like it was going to be very dumb, but it actually turned out to work pretty well, okay? So I'm just going to do that here, right? And let's assume that what we have is one attribute per word position in the document, okay? So if the document is 1,000 words long, I have 1,000 attributes, okay? And the attribute in each position is the word in that position, okay? So if I have, let's say 10,000 words in the language, in general I have more, but let's say I've restricted this to the, 10,000 most interesting ones, I have attributes with 10,000 possible values, right? So this is a lot of values, right? And then my learning, right, is going to consist of using my training corpus of documents to estimate P of plus, P of minus, and then the probability of each document, given that it's positive, meaning interesting, or that it's negative, okay? So far so good, very straightforward. So now let's make our naive-based assumption, right? This is the first thing that we're going to do to make this problem tractable is, I'm going to assume that my probability of the document given the class is just the product over all the positions in the document, right? So I just have to run through the document of the probability of the word that I'm going to see in the test data or that I see in the training data at that position, right? What is the probability that the first word in the document is the? Probably pretty high. Right? What's the probability that the first word is a verb? Well, probably not, because usually documents don't start with verbs and so forth. Okay? But now we need to make one more assumption, which again is a brutal oversimplification, but for the same reason is not going to hurt us that much, which is I'm going to assume that the probability is not going to vary with my position in the text. In real text, of course, as in the example that I just gave you, the probability varies with position. Like, for example, the is quite likely to be a first word and the verb isn't. But we're going to, ignore that and assume that the probability stays the same throughout. Okay, so this greatly simplifies our problem, right? Because now, instead of having to estimate 1,000 things, I just have to estimate one for each word. And again, this is basically, treating your documents as, instead of having sequential structure, just being a random jumble of words, right? Very unrealistic, but it's not going to hurt us. And so with those two assumptions now, we have a complete algorithm, and this is what we're going to ask that you guys implement for spam filtering. So let's say these are my examples, right? My examples are a set of training documents. Let's say spam and non-spam. And V is the set of classes that I want to predict, in this case spam or not spam, or interesting or not interesting. Or if you have 20 topics, then the 20 topics are the classes. The first thing that you do is you take all your documents and you collect all the words and tokens that appear in them. By the way, when I say tokens, it's because non-word tokens are often very informative. Depending on the domain, but for example, a traditional example in spam filtering is if you have many exclamation points in a row, right? If one of your tokens is 3 exclamation points, this is a really good sign of spam. Because most people don't send emails with 3 exclamation marks, but in spam, if you have free in capitals, followed by 3 exclamation marks, there's a good chance this is spam. This also caused some people that had a tendency to send, messages with a lot of exclamation marks and capitalized words to get their messages classified as spam. But these days things are more sophisticated than that. So tokens can be informative, not just words. So then my vocabulary, right, is just all the distinct words and tokens in my examples. And now the first thing that I have to do is compute all my class prior probabilities and all my conditional probabilities of the words given the classes. Okay? So, for each target value, for each possible class, I do the following. I first collect all the examples of that topic, say all the pages that are about sports. Okay? And then my prior probability of the class is very simple. It's just the size of that set over the size of the entire corpus, right? If I have 10,000 pages and 1,000 are about sports, the probability is 0.1. Okay? And then the next thing is to deal with the attributes, so we concatenate all the members of, say, the class sports, right? I'm not going to care which document they came from because this is all just going to boil down to counting, right? So I count the total number of words in the documents of that class, right? And remember, duplicate words count duplicate times because I care whether a word occurred, once or twice or 50 times, right? That's going to make a big difference to my probabilities, okay? And then for each word in the vocabulary, right? If nk is the number of times that word occurs in the documents, in the total concatenated text of that topic, then my estimate of the probability is just going to be nk plus 1 over nk plus the size of the vocabulary. Okay? So this is just my simplest possible Laplace estimate. Right? If I haven't seen any data, then it's just 1 over the size of the vocabulary, which seems reasonable. Right? I'm just uniformly generating words. Right? That's the principle of indifference. Okay? But if I've seen a lot of words, then this just becomes my maximum likelihood estimate. It's the fraction of the words that are, that are that word. Okay? Notice this thing of concatenating all the documents. What I'm trying to say here is that I'm not going to care which document things came from. I'm just going to treat it all as one big document. Okay? And notice that this is not the only way to build a classifier for text or a spam classifier, but it's the easiest one. If you want to do variations from this, you're more than welcome to try them, but this is at least one way that you can do things that works reasonably well. Okay? Questions? Okay, so here's our classifier finally, right? Then you do the usual prediction. No need to repeat that. Here's a concrete example just to persuade you that this stuff really works. Let's just take 20 newsgroups from Usenet and 1,000 training documents from each one. So this is not a big data problem. This is a small data problem. And here they are, right? Comp.graphics and so on and so forth, right? We apply this exact algorithm that I just described. This is the reason I'm using this dataset is actually publicly available, right? This is a dataset that you can actually play with. You can download it from the web and you can use it, right? And it's small, so it's easy to play with. The accuracy of naive Bayes on this dataset is 89%. Notice that I have 20 newsgroups with equal frequency, so the base rate is 5%, right? If I just randomly guess the class of each, the topic of each posting, based only on the frequency of the class, I will only be right 5% of the time. Okay? Or if I pick the most frequent one, in which case they're all equally frequent, so it can be any one of them. But the default accuracy here is just 5%, right? This is where having many topics is a more challenging, interesting example than just having two things, right? So the base prediction here is just 5% accurate. Naive Bayes gets you all the way from 5% to 89%. Now later we're going to look at things like support vector machines, which are the state of the art. And let's say on this data set, I don't remember exactly how well support vector machines do, but let's say they get you to 95%. Right? It's very hard to get to 100% because at the end of the day those assumptions are false and the structure does matter. Right? But the key thing to remember here is the following: is that naive Bayes, for all its simplicity, gets you from 5% to almost 90%. And then all the very fancy, latest, greatest optimization machine learning techniques give you another 5%. Okay? And this is not uncommon. Maybe they give you another 10%, right? Depends on the problem. But the bottom line is, a simple algorithm, carefully applied, can give you most of the gains that you're going to get. Okay? So it's very much worth knowing about. So here's a little example of such a story. Here's a graph, right? And again, this is from real experiments, comparing naive Bayes with using TF-IDF, right? People in information retrieval, have spent many years developing, these kinds of measures and techniques for these problems. And, TF-IDF has been, the winner, okay? And the thing is that naive Bayes, out of the box, is already beating TF-IDF, or essentially doing as well as TF-IDF. If you with less data, TF-IDF is slightly better. With more data, naive Bayes actually starts to dominate. And then here's actually it's a combination of naive Bayes and TF-IDF. But the bottom line is, think of all those years that people in NIR spent, working on things like TF-IDF, naive Bayes. You run it on some data, and it's as good as that. If you think this example is a little bit shocking, you should look at medical diagnosis. Doctors spend all these years in college learning how to do diagnosis, and then I give you a database of patient records and whether or not they had diabetes or not. You run naive Bayes on that, and it beats the doctor. People also in the early days of AI, right? One of the things that they did was build these medical expert systems that had lots of rules. If this and this, but not that, then they have diabetes. This basically beats that out of the box most of the time. This is a really good illustration of the power of data. A really simple algorithm like naive Bayes. You give it, a reasonable amount of data. It doesn't even have to be a lot, right? There's lots of these medical data sets available on the web. They typically have, say, 1,000 or even less examples. Naive Bayes with that number of examples is enough to do better than doctors. People have done some studies where they compare naive Bayes and Bayesian networks, which we're going to see in a little bit, and they tend to do better than people, despite the fact that doctors have all those years of training. So this is a good illustration of the power of machine learning. Okay. Don't tell this to your doctor because they might get demoralized or they might get furious. But this is the case. Doctors, of course, have a big advantage in that they have access to information that naive Bayes doesn't, right? They can see how you're looking that day, and they maybe know more information about you than just the tests. The big problem with people, though, is that they are very inconsistent. If the doctor's in a good mood, right, they might be more likely to give you, one diagnosis than if they're in a bad mood. In fact, there was like this study that I don't know if you guys saw in the press. I think this was done in Israel or somewhere. That if after lunch, if you are on trial for something, right? You want the judge to make the pronouncement after lunch, because then they're in a good mood, and they're much more likely to acquit you or give you a lenient sentence than when they're hungry and grumpy. Also, the end of the day is bad, right? They just want to, they want to be done, and they're in a bad mood, and right. So, naive Bayes doesn't have that problem. Right, naive Bayes doesn't get hungry and it doesn't get in a bad mood. So, anyway. Any questions about naive